Hello, welcome back. Now this will be actually like the I think sixth time I'm recording this particular question because there were interruptions or my hard disk went out of space. But never mind that. Welcome to my channel. Now if you are watching this for the first time, please look at part 2 and part 1. Those will be the discussion of the questions that came before this. Right, if you're watching this as a continuation and you're my student, please make sure that you have your green pen and a paper with you. So pardon the mess here because I've written over this several times in several recordings. Okay, let's start. Now, 4 identical objects were heated to a temperature of 90 degrees Celsius. Each one was placed into a beaker of water as shown below. So all these 4 are the same type of object, same material, and they're heated up to the same temperature. As you know that a hot object will lose heat to its environment. Alright? And notice that we're just going to cover parts of it. So we just focus on one part of this diagram, okay? Let's ignore this first. Now, why do you focus on this? Because these 2 beakers of water are at the same temperature. The difference is they're at different volumes. So imagine you want to heat up less water or heat up more water. Which beaker of water will feel hotter first? Naturally this one, right? Because it has less water to gain so much more heat. Here, there's so much more water to gain the same amount of heat. Think of the 90 degrees like money, okay? So it's like $90 given to a few students or $90 given to a lot of students. So everyone will get more and get faster. You receive it faster. So it'll be hotter faster. And why I talk about faster? Because the temperature of water was measured after 3 minutes. So they are given the same amount of time to lose heat to the surroundings. And so in the same amount of time, alright, the water here will be much hotter than this because it takes a lot more heat to heat up a lot more water. Let's look at the other side now. In this diagram, you have again 2 containers at the same temperature of 50 degrees Celsius and they are different volumes. So same reasoning, there's more water here, so it takes it takes more heat to heat up so much more water to the same temperature as this. So after the same amount of time, the water here will feel hotter than this. Now comparing these two, the water here is hotter than this, the water here is hotter than this. But which one is hotter than which one? Now this beaker here has water that starts off hotter at 50 degrees Celsius at a higher temperature compared to this at 15 degrees Celsius. So this water here, since it started off at a high temperature and gained more heat when it was at a high temperature, this is hotter than this. So Y is the hottest. If Y is the hottest, the answer is clearly 1. Y is the hottest. Hottest would be here 2. Okay. Now this is you're very lucky that you can get to the answer, but just by reducing one option. Usually it's not so easy to get an answer. You need to process both sides. So if I have a chance to design a question, I'll probably put another Y somewhere so that just to let you process the part where you have to come up with the idea that the conclusion that X is the one with the lowest temperature. X is this one. It is at the lower temperature compared to this. This is a cooler one, right? This is lower temperature than this to begin with. So of course this will be cooler than this after 3 minutes. Okay, let's go on to the remaining 3 questions. Ball A was released on a curved track from point A as shown in the diagram below. From A, it will swing all the way to B. Now, if you first start here, before releasing the ball, the ball wasn't moving, so KE is 0. And this is the highest point compared to all these remaining 3 points. So the gravitational potential energy or GPE is at the highest or the maximum. As it rolls down, the GPE is converted to KE, right? GPE converted to KE of the moving ball. And so the GPE will start to decrease and KE start to increase. This is the lowest point on this curved track. Excuse me. The lowest point means the GPE cannot go any lower. It's at the lowest or the minimum. And KE will be at the maximum here. It's regain as much GPE as possible from the ball. Now it starts to move up. As it moves up, the KE is converted to GPE. As the kinetic energy of the ball makes it move higher and higher, this KE is converted to GPE. Until eventually it stops moving, then KE becomes 0 and GPE becomes maximum at this point. So which is the correct answer? The ball has the most kinetic energy at point C. Kinetic energy is at the maximum. Okay. Now last 3 questions, 26, 27, 28. I think I miscounted. The diagram shows part of a hydroelectric power station. Water flows from the highest point and turns the turbine at C. Electricity is then generated at B. So basically this is a very good question. It's really given good for you because the energy conversion is already given to you. All you need to do is convert it into the form like this. So GPE of the water, so you must start with GPE, right? Is converted to the KE of the running water. So KE, and converted to the KE of the spinning turbine. KE, and then converted into electrical energy in the generator. Electrical energy. Answer is 2. The statement below shows the properties of substance H. At 340 degrees Celsius, H can be compressed. At 120 degrees Celsius, H have no definite shape. Now we talk about properties of materials, right? Solid, liquid, and gas. So we're talking about the volume. Solid has a fixed volume. Liquid has a fixed volume. But gas has an indefinite volume. That means that the volume can change because you can compress it. So which one cannot be compressed? Solid cannot be compressed. Liquid cannot be compressed. You did that in your syringe experiment. You put in some liquid in the syringe and you try to press down on it with your finger here, blocking the nozzle. And the liquid cannot be compressed. You cannot press the plunger in. But if this is gas, then you can actually compress part of the gas. And gas can be compressed. How about shape? Solid, definite shape. Liquid, there's no fixed shape. No fixed shape. The liquid takes the shape of a bottle or a container. Gas, no fixed shape. Alright, solid, there's a fixed shape. At 340 degrees Celsius, H can be compressed. They are saying that, okay, at this one, H becomes a gas. That's why it can be compressed. It becomes a gas. In other words, it has boiled. It has boiled, or it has boiling point of H is definitely above or at 340. So, if this is the boiling point of H, therefore, any temperature above this, okay, what is the boiling point of H? It cannot be this, and this cannot be higher than 340. What can be the boiling point of H? It cannot, can it be 200? It definitely cannot be 360, Alright, because this means that at this temperature, H is already a gas. So it must have converted into a gas before 340 or at 340, not above that. So it must have boiled early on. So it's either 1 or 3. Next one, H has no definite shape but has definite volume. So they are saying this is a liquid. So 120 degrees Celsius, H is a liquid. So which of these is a liquid within that range? So if I draw out this idea, 80 degrees Celsius melting point, it must have melted, then it becomes a liquid. So this is the answer. So let's draw it out for you to see. Let's say at 80 degrees, if this is the melting point, let's say at 80 degrees, it's melting point. At 280 degrees is the melting point, at 200 degrees is the boiling point. So this is how I'm going to check my answer. Okay, if this is true, anything below this will be solid. After it has melted, it becomes a liquid. When liquid boils, it becomes a gas, right? So if my answer is 1, I'm saying that at 340, H can be compressed. 340 is here, right? Gas can be compressed. This is true. At 120, H has no definite shape and definite volume. So at 120, H is a liquid. 120 is between these two. It's a liquid. This checks out, so my answer 1 is correct. Ready now? Last question. This is about your forces. An unstretched spring is shown in the diagram below, unstretched. So it's not yet compressed. A metal bar or it's not yet stretched. So in an unstretched spring like this, there is no elastic spring force yet. Because elastic spring force is the force that makes the spring want to return to its original shape and length. Since you never stretch it, you haven't stretched it, of course, the length is just that. There's no change in the length. A metal bar is placed on top of two such springs, and then it becomes compressed from 14 cm compressed to 11 cm. A weight is then placed at various positions on top of the metal bar. We shall show the correct observation. If your metal bar has mass, alright, and then it presses down on, and it has weight. Weight is a force. Weight is a force, okay, and the force presses down on the spring. And the spring has an elastic spring force that pushes back against it. Remember, this is nothing about friction. No friction here. If you now put a weight on top, a weight is put on top, then there's even more weight. It's the weight of the object plus the weight of the bar. The compression should be even more than 11. So I should see it more. Okay. So this one firstly doesn't make sense because after put a weight it becomes even. It goes back to its original length. This is definitely wrong. I'm putting weight on one spring. How come the other spring also compressed the same way? Because now the weight is pressing down here. There's no weight pressing, only the weight of the bar is here. But here is weight of the weight plus weight of the bar. It's wrong. You put a weight here, this actually be compressed. This is wrong. You put a weight here, this is compressed. This one makes sense. Okay? This is the answer. Answer is 3. Thank you for sticking in here all the way to the end. I wish you all the best in the exams that you're preparing for, whichever year you are in right now as you're watching this video. Take care. Goodbye.